Right, so guys, holy smokes, right? 3 days. Guys, 3 days from now, this slide, right? You got them in front of you. 3 days from now, this slide, 3 class periods from now, this slide is going to come up on the screen and we're done for the year, right? It's how we end every day with homework. 3 days from now, homework, and that's never going to happen to you again in this class. We're done. Of course, we're just getting started. But guys, we have 3 days left of new material. So let me give you the overview for this unit. So guys, with chapter 20, if you've summarized it, you're aware of this, but if you haven't, let me cast a broad net for a second. So guys, chapter 20 is all about electrochemistry. We're going to break it into 3 chunks. So guys, today what we're going to do is we're going to talk about the fundamentals of electrochemistry and balancing what are called redox reactions. You'll see, it's nutty. Nothing like you've seen before. So guys, that's going to be our day today. Then when I see you on Tuesday, we're going to spend the entire day and we're going to talk about how batteries work. You will see on the AP test practices, the AP authors love battery questions because they can ask you all sorts of interesting things about equilibrium, about oxidation reduction, about Gibbs free energy. They can go all over the place just by talking about batteries. They like it. Then guys, the third day, not surprisingly now, is going to be all about spontaneity, Gibbs free energy, and electrochemistry. So guys, today is foundational. Today is balancing redox equations. Tuesday's batteries. Thursday's spontaneity. That's the year. You guys ready to go? Okay. So guys, here's what you've then got in front of you. So the packet that I gave you, which starts with this thing that says background, is then missing this page. So it's kind of like this goes on top of that, if that makes sense. But guys, let's get started by talking about some foundational stuff about electrochem, which is therefore oxidation reduction chemistry. Now guys, here's the trick. It's really, really important that you engage in the homework that you're going to get tonight over the next couple days. The reason is this. Guys, you're going to run into these terms, oxidation and reduction. So backing up a little bit, guys, these are really important terms for you to understand. You're learning a new language. So guys, enough of you have siblings or friends or neighbors that are on missions, right? That you understand how the mission process works. So you get called, you go and you first go to the MTC and you hang out at the MTC for a while. And what do you do at the MTC? You learn, you learn to teach, but then you also typically learn, depending on where you're going, a language, right? But you understand that that little bit of learning that takes place at the MTC is not really where you learn the language, right? Where do you actually learn the language? In the field, while you're out there amongst the people. Now, guys, have we had this conversation before? How, and this is not just LDS missionaries. Guys, there's a moment in time, and maybe you're aware of this, and for some of you, you'll have this experience. There's a moment in time where you know that you have learned the language of the country that you're in. Do you know when it is? When you dream in that language. Because guys, when you start dreaming in that language, it means you're no longer translating. It means your thoughts are generating in that new primary language. Guys, here's the deal. You got to get to the same place with oxidation and reduction. You cannot be in the position where you talk about oxidation and reduction, and before that word comes out of your mouth, you go, okay, oxidation means the losing of electrons, and if you're losing electrons, then the charge becomes more. You can't do that. You've got to be like conversant with this to the point where oxidation just comes off your, you can look at something and go, that's being oxidized. You can look at something and go, that's being reduced. And guys, the only way to do that is by immersing yourself in the homework so that you actually have the experience of thinking in this new language. So with that said, guys, let's get going. So when we talk about in which there's an exchange of electrons. And so guys, when we talk about this exchange of electrons, what we're actually looking for is changes in charge. Now guys, do you remember when we talked about this? I don't even remember what chapter it is. Remember the aqueous chemistry unit? What chapter was that in? Is it 3? Yeah, I think is it 3? 3 is stoichiometry, must be 4. Yeah, so guys, 4, remember chapter 4 was all about aqueous chemistry. And we talked about acid-base reactions, we talked about precipitation reactions, and we talked about electrochemistry, and we talked about oxidation and reduction. And guys, back in September when we went over this, we said this is going to be the end of the year as well. Well, that's now. So guys, when we talk about this stuff, it is stuff that we touched on briefly, but we're going to go deeper. So guys, when we talk about oxidation reduction reactions, we've got electrons moving back and forth. Kind of in the same way that in an acid-base reaction, you've got protons moving back and forth. In electrochemistry, you've got electrons moving back and forth. So guys, this then is the idea, and you might want to tear this apart. So guys, as these electrons are transferred, they're always transferred from the atom that's oxidized to the atom that's reduced. So guys, let's talk. Why do we call then this oxidized and this reduced? If you understand the reasoning, I think it'll help you understand how to make sense of this. So guys, first of all, well, maybe we should say this then. So oxidation then refers to the loss of electrons, and reduction refers to the gaining of electrons. So guys, why do we call losing electrons oxidation, and why do we call gaining electrons reduction? Let's do losing first. Do you remember? I think we did talk about it. Go ahead, Doug. Exactly. Oxygen is an amazing electron stealer. What 2 reasons would make oxygen a really good electron stealer? High electronegativity, and 2, small, which is also good for you. It's also related to electronegativity. But guys, what else? It's got space. It's got room for 2 electrons, and it's plentiful in our environment. And so guys, when they were originally studying reactions that involve the loss of electrons, they saw that oxygen caused that to happen in a lot of elements, so they called it oxidation. By the way, guys, you actually know a lot of these reactions by another name, rusting. Guys, that's all rusting is oxygen pulling electrons off of metals. When oxygen pulls electrons off of metals, the oxygen becomes negative, the metal becomes positive, and you get an ionic bond that we call rust. Yeah?
So I just have a question about water. Why is that when you put water on something?
Yeah, that's a good question. I hesitate to say this, but I'm gonna. Water kind of works like a catalyst in this process. Not quite, and we'll talk about it a little bit, Thursday? But it's kind of like a catalyst. It does promote, so in that sense, it is a catalyst. It promotes the reaction without getting involved. The chemistry of it's a little bit weirder than that, but it kind of functions as a catalyst. Go ahead, Elisha. Oh, I think so. I would think that to a metallurgist, somebody that really studies what metals do, They would probably say no, but in my limited experience, I believe it is. I believe that tarnishing and rusting are the same things. But if you told me I'm wrong, I wouldn't be shocked. But I really believe. So we can say this: I believe that tarnishing is an oxidative process. It may not be exactly the same chemistry as rusting, but I believe it is oxidative. So, okay. You guys good on why we call oxidation oxidation? So guys, why do we call reduction reduction? Charge goes down. Whatever it is that gains electrons, electrons being negative, the charge goes down. So guys, we call reduction reduction because the thing that's being reduced, its charge goes down. Does that sit okay? Okay, now did any of you go to the University of Utah for the summer program last summer? None of you did? Okay, so this is the way that I think about this, and then I'll share with you the way they teach this at the U. So guys, for me to keep this straight, I never want to live here. That's too much thinking. If you have to spend the time, in a couple days, if you have to spend the time to think oxidation, you're going to be in trouble. Guys, this is where my brain goes first. This is how I keep this straight. The charge of the atom that's reduced is reduced. So instead of picturing electrons moving around, I'm picturing charges. So charges down is reduction, charges up is oxidation. Guys, the way that they teach it at the U, and I don't know if I shared this with you, the way they teach it at the U, did I show you this? Oil rig. Do you guys like that better? To me, that's just corny. But it's oxidation is loss, reduction is gain. If you like it, use it. But guys, in either case, your goal is to quickly wean yourself of all of this stuff so that you can just look at these processes and go, that guy's being oxidized, that guy's being reduced. What you're going to find when we do batteries is many times it involves things going into solution, and we'll talk more about that next time. So you guys okay with the fundamentals? Okay, so guys, one more thought before we move on then, and it has to do with the idea of agency. You'll notice that it's underlined. And guys, you may want to pick this apart in your notes. So I think it's clear that in order for there to be oxidation, there has to be reduction and vice versa. In the same way that for there to be an acid, there has to be a base, right? If something's going to lose a hydrogen, it has to go somewhere. Well, guys, in the same way here, if something loses an electron, somebody's got to pick it up. So these things always happen in pairs. And so we talk about it this way. And we say oxidation is loss, and we say reduction is gain. But understand, we can also change our focus. So guys, imagine that I'm a metal and I'm being oxidized. What's happening to me? If I'm being oxidized, what's happening? I'm losing electrons, but where do they go? Somewhere else. What happened to that guy? He got reduced. That makes him a reducing agent. So guys, we can look at this through either lens. When we talk about oxidation and reduction, we're talking about one substance, but we can also talk about agency, which turns the attention to the other substance. So if I'm being oxidized, I'm losing electrons, but whoever's taking my electrons is being reduced, and we call that the reducing agent. And then similarly, guys, if I'm being reduced, I'm taking in electrons. Whoever lost the electrons is being oxidized, and that's the oxidizing agent. Did you guys notice how reduction and oxidation just roll off my tongue? Guys, you've got to be at the same point very quickly. You've got oxidation, reduction, you got to get to that point quick. But guys, understand then, this idea of agency simply turns our focus to the other guy rather than being on the substance that we're looking at as being oxidized or reduced. You guys okay? Does that settle? Go ahead, Jeanette. Yes, say that again. Say that again and let's talk about it. The one that takes electrons is the oxidizing agent. Because if I take electrons from you, what am I doing to you? You're being oxidized. So when we talk about agency, it's not about what's happening to me. It's what I'm doing to you. So if I'm the oxidizing agent, I'm making you be oxidized. That means you're losing electrons. So what's happening to me? I'm gaining electrons, so I'm being reduced. Do you see? So the word agency means what is this guy doing to the other guy? Does it make sense now? Is that okay? Yeah. Exactly. It's the reverse logic, because it's whatever you're doing to that guy, the opposite is happening to you. Yeah. So the oxidizing agent's being reduced, the reducing agent's being oxidized. Is that okay? Okay. So guys, with that as background, this then is where we're headed. So what we need to do now is we need to bring these ideas of oxidation and reduction to bear on actual chemical reactions. So guys, I don't remember. So these are your notes now, right? Okay, so I gave you the balanced equation, but guys, you'll notice I left out some of the answers. So we're going to fill those in. I didn't want to just feed you the answers. So guys, the idea is this. If we've got this balanced equation, and you're going to need to be writing now. Guys, this is an oxidation reduction reaction. We call those redox reactions. But if I hadn't told you this was redox, what kind of reaction would you know this to be, given what you learned last year? Single displacement. Guys, almost all single displacement reactions are redox. If you see a single displacement reaction, your brain should be going, I'll bet that's going to be redox. Guys, the question is why? The answer is because electrons are being exchanged. Then the question is, how do we know? And the answer is, let's give these things their oxidation numbers. So guys, assigning these with me, let me switch to red. Guys, hydrogen is +1, chlorine's -1, right? Right off the periodic table. What about zinc? Do you remember? What is the oxidation number of an element in its elemental form? 0. So guys, using that same logic, assign oxidation numbers to the guys on the right. So guys, chlorine is still -1. What does that make zinc? +2. And then guys, what about diatomic hydrogen? That is its elemental form, so it's 0. Does that make sense? Okay. Now guys, let's answer the questions that are on the slide. Only we're not going to look at the slide. Let's just talk about it. So guys, the idea is this. Whose charge didn't change? Chlorine, right? You want to guess what that makes chlorine? Spectator. If I had asked you to write the net ionic equation, you would have known that chlorine was a spectator anyway, because it starts aqueous and it ends up aqueous. So guys, by your understanding of spectator, chlorine is the spectator, chloride is the spectator, because it starts and ends up aqueous. But the reason that that's the case is because it doesn't gain or lose electrons in this redox reaction. So guys, at that point, let's connect these together. So these are the two that did gain or lose electrons. So guys, let's talk about zinc. Did zinc gain or lose electrons? So it started at 0 and its charge went up, right? So it went to +2. So its charge went up. So did it gain or lose electrons? Lost electrons. So this lost 2 electrons. So now guys, let's look at the hydrogen. Hydrogen started out at +1 and it ended up at 0. So what happened to hydrogen? It gained electrons, but this gained 1 electron. So now guys, we've got all sorts of stuff to talk about. So guys, first of all, this. Which substance is oxidized? Zinc. And guys, again, you should be able to look at that and just go, boom, whose charge went down, who lost, however you think about it. You've got to get to the point where you can just instinctually look at this and go, zinc got oxidized. If you're not there yet, which I don't expect you to be, the idea is that zinc lost electrons, and we know that because its charge went up. Now, guys, which substance is reduced? Which substance is reduced? It is not hydrogen. It's not HCl. Hydrogen ion. Guys, that is very, very important. Hydrogen ion is reduced. And you're like, well, those are the same. No, guys, no, they're not. What is hydrogen ion? A proton. What is hydrogen? Hydrogen is two atoms bonded together. Guys, hydrogen ion and hydrogen gas couldn't be any more different. They're not even close to interchangeable. So guys, hydrogen ion is the substance that's being reduced. It is not hydrogen, it's hydrogen ion. Does that make sense? Okay, now guys, this. So zinc lost 2 electrons. Hydrogen ion only gained 1. Where did the other electron go? There's 2 of them. Guys, the stoichiometry goes like this. So this gaining of 1 electron is times 2 hydrogens. So 2 hydrogen ions are both reduced to hydrogen gas. So guys, the way that we would say it is this. We would say zinc metal is oxidized to zinc ion. Hydrogen ion is reduced to hydrogen gas. So guys, as you're thinking through this, let me make a suggestion, and you're going to feel really stupid doing this, but try it. Guys, when you're working on your homework over the next couple nights, try reading your answers out loud. Seriously, you're going to feel stupid, but guys, you'll find that if you'll actually say these things rather than just read and write them, it'll actually cement them in your memory better. So guys, again, zinc metal is oxidized to zinc ion. Hydrogen ion is reduced to hydrogen gas. So guys, let me ask you a question. If you could see this reaction take place, what would you see in the beaker? What's in the beaker? Hydrochloric acid and a chunk of zinc, right? The zinc is a chunk. The hydrochloric acid is actually aqueous in solution, right? So guys, what would you see as this reaction took place? You'd see 2 things. You'd see bubbles, and what else would you see? Not a precipitate. What else would you see? You can't see the zinc dissolve because zinc solution is colorless. What would you observe with your eye? It would still be clear as well. Not a color change. You would see the hydrogen gas. What else would you see? There isn't a precipitate. That's it. You'd see the chunk of metal get smaller. Guys, and that's not trivial. Because many times what you're going to see is the oxidation of metal, and this is critical for understanding batteries next time. Guys, many times the oxidation of metal, sorry my writing's so bad, but guys, the oxidation of metal involves a solid elemental metal dissolving into water as an ion. So this zinc metal literally gives up electrons. As this zinc metal gives up electrons, where do those electrons go? To the hydrogen. Then they bond together and they go away as hydrogen gas bubbles. And as that happens, this zinc metal is then going into solution as an ion. So guys, that's another thing to try to cement in your understandings, is that many times the oxidation of metal involves a solid dissolving into solution as those metal atoms lose electrons. Do you see how that kind of fits? Okay. So, guys, I believe we've answered all the questions. What's being oxidized? Zinc. What's being reduced? Hydrogen ion. And then what do we know about the amount of electrons that are being lost and gained? What do we know about the number of electrons that are lost and gained? They're the same, and they have to be. Guys, we are about to talk about the law of conservation of electrons. Seriously, all of the electrons that are lost have to be gained and vice versa. We don't get stray electrons. We don't get missing electrons. Guys, you've always got to balance electrons, which frankly is what makes balancing redox reactions so frustrating. So guys, any questions on this? You guys good? Okay, so where does that take us next? I'm just going to click through these. Do you need to fill in the blanks? You're probably okay, right? You've got all of that and more in your notes? Okay, so guys, here we go. We are now going to learn how to balance redox reactions. Guys, I've been teaching this since 2002. Holy smokes, 17 years. I have only done this error-free once. It hasn't always been the same equations. But guys, I've only done this without error once. It was last year. We had a little party. So, guys, understand, well, we'll see. Hopefully I don't screw it up this year. But guys, what I'm telling you is the steps to this get a little crazy. So guys, you know how to balance equations, right? Reactants, products, they've got to be the same. Law of conservation of mass. Everything that goes in comes out. You guys have been balancing equations for more than a year. Well, guys, you are now going to learn to balance redox reactions. And there are steps to these. Let me show you. Guys, these are the steps. So up until now, we've discussed balancing equations by simply obeying the law of conservation of mass. Everything that goes in comes out. And guys, that's still important. Everything that goes in has got to come out. But we also have to include electrons now. All of the electrons that are gained have got to equal all the electrons that are lost. So in order to balance equations, when we have to account for electrons, here's the steps, you guys. Step 1 is balance the half reactions. That means nothing to you, but it will in a minute. Then guys, after that, balance all the other elements. Then after that, balance oxygens by adding water. Then after that, balance the hydrogens by adding protons. Then after that, balance the charges by adding electrons to the side with the greatest overall positive charge. Then after that, multiply each half reaction so that the electrons balance. Then after that, add the two half reactions together and simplify. Then after that, if it's in a basic environment, add hydroxides to get rid of all the additional hydrogens. You guys ready to try this? Yeah. Yes. You mean you don't want to write all that down? Me neither. All right. So guys, in order to be able to do this, what we need to do is we need to talk about half reactions. So guys, let's, check your work and then have a party. So, or curl up and I forgot to put that. Yeah. Okay. So guys, let's talk half reactions. Go back here. I'm going to show you what half reactions are, and then this will make more sense. We're going to switch to blue. Is this familiar enough to you that we can just talk about it? Okay. So, guys, oh no, sorry. Oh gosh. Sorry. There we go. Okay. So guys, going back to this process, think about what we established. We established that zinc is being oxidized. We established that hydrogen ion is being reduced. Previously, we established that you can't have one without the other. Does that make sense? Okay, so guys, this is half reactions in a nutshell. Guys, this is the whole reaction. But what we can do is we can take this whole reaction and we can break it into two halves. That's where the name comes from. We're going to break this into two halves. But guys, if we're talking about oxidation reduction reactions, it makes sense to break them in half so you've got the oxidation and you've got the reduction. Does that make sense? Okay, so guys, which one is the oxidation? The zinc or the hydrogen? The zinc. So guys, do this with me. Zinc. It's weird to have that happen and not have Mark chuckle. I don't know. So guys, we're focusing on the oxidation reaction. So zinc is being oxidized. Now guys, what's happening to the hydrogen ion? It's being reduced. So let's do this. So, because I'm going to just go over here. Yeah. So guys, hydrogen ion is being reduced. So here we have our oxidation. Here we have our reduction. Now guys, let's do the reduction first because this is going to make more sense. So guys, we have two hydrogen ions, right? Yes. We have two hydrogen ions. What does it mean that those hydrogen ions are being reduced? What's happening to them? They're gaining electrons. How many? 2. And that makes hydrogen gas. That is the reduction half reaction. Now guys, let me show you the oxidation half reaction, but please don't write until I tell you because I'm going to do it wrong. Guys, watch. What is happening to this zinc atom? It's being oxidized, which means what? Please do not write this down. So this zinc atom is losing electrons. How many electrons? 2. So losing 2 electrons, and that forms zinc ion, right? That, however, is not the way we write the oxidation half reaction. We do not write it as a losing of electrons. We actually move the -2 electrons over here. So guys, what we do is we think about it this way. We think about zinc atom creating zinc ion, and when it does, 2 electrons come out. So we represent the loss of electrons not as a loss in the reactant side. We just think of it as being a product. And maybe you've never thought of it that way before, but guys, when we write balanced equations, have you noticed that we never have minuses? It's always this and this, and if something's being lost, it just makes it a product. So guys, the idea here then is when we write these half reactions, we always write them with pluses. So the reduction half reaction is plus electrons. The oxidation reaction is also plus electrons. They're just on the product side. Doesn't that make sense? That oxidation is losing electrons, so they're being produced. Okay, so guys, relative then to the notes that I gave you, let me get on the right page here. So guys, relative to the notes that I gave you, these half reactions then, the half reactions then are these. So zinc turns into zinc ion plus electrons. The reduction is 2 hydrogen ions gaining 2 electrons to make hydrogen gas. So guys, this might be a good point to make this note. In an oxidation, the electrons are a product, and in the reduction, the electrons are a reactant. You guys okay? Okay. So guys, with that said, here we go. So guys, going up here, these are the steps. We are going to carry out these steps to balance two reactions. I've given them both to you. Here is the first one. But guys, before we do this, I need to calibrate my board, because this is going to be a mess if I go to do this and my board freaks out. So, smart settings, orient and calibrate. Guys, this will take just a second, and then we're going to do this. Okay. Easily impressed. Here we go. So, guys, step number 1. Draw a line down the middle of your paper. Don't go all the way to the bottom. Step number 2, write the half reactions. Now, guys, here's the deal. You know how when you play chess, the move doesn't count until you take your finger off the piece? Same deal. It doesn't count as a mistake until I take my pen off the board, okay? I really am hoping for 2 years in a row. This is weird because we've only got one product. So what that means is this turns into this and that turns into this. So we have the same product for each half reaction. So guys, our first half reaction is this. I minus yields I3 minus. Do it. Don't get all ahead of yourselves. Then, guys, our other half react. That's not in the middle, is it? It'll be good. No, it won't. No, you don't understand what's coming. You should be nervous. I minus yields I3 minus. And our other half reaction is IO3 minus yields I3 minus. Okay, I haven't made a mistake yet. Okay. Now, guys, and I'm even going to read the steps. Step number 1, now in balancing, we've got the half reactions. Okay. Balance all the other elements besides hydrogen and oxygen. So we have 1 iodine, 3 iodines. So guys, we're going to go 3 I3s yields 1 I3 minus. Now guys, learn from my experiences. When you're balancing these half reactions, rewrite them progressively for every step. So guys, we've got 1 iodine here, we've got 3 iodines there, so we go 3 IO3 minuses yields I3 minus. I feel like I've already screwed up. Am I okay? Wait, I did screw up. No, I didn't. No, I'm okay. No, I'm good. I'm okay. Okay. So guys, 3 iodines, 3 iodines, 3 iodines, 3 iodines. Good. Now guys, next step. balance oxygens by adding water. So guys, we have no oxygens here, right? Just trust me on this. Write it down again, just like you did before, because you really want to keep this in lockstep or it's going to fall apart. Okay, so now we have oxygens in our right side reaction. How many? How many oxygens on the right? 9. So guys, what we've got to do is this. 3 IO3 minuses yields I3 minus plus 9 molecules of water. Good? Okay. Now hydrogens by adding protons. No hydrogens here. Rewrite it. Now hydrogens here. 18. So 18 protons plus 3. And guys, notice that's protons and not hydrogen atoms. 3 IO3 minuses yields I3 minus plus 9 waters. I'm starting to get confident, but that means I might be in trouble. Okay, we're good. So guys, now I'm going to switch pen color just to let this stand out a little bit. Okay, so now guys, the next step. Balance charge by adding electrons to the side with the greatest overall positive charge. So think about it this way. We're going to figure out, in each of the half reactions, we're going to figure out the charge imbalance. Then, whichever one has a higher charge, we're going to add electrons to that side to bring it down to whatever the other charge is. So guys, we've got 3 negative 1s. So what's the negative charge? Negative 3. Do this with me. Now guys, on the right-hand side, we have 1 I3 with a negative 1 charge. So this is negative 1. So guys, if you picture it this way, imagine that this is 0. Just do this with me. So if this is 0, this side is negative 1, this side is negative 3. So what do we need to do to make them equal? We need to push this side down to negative 3. So what do we need to add? 2 electrons. So guys, we go then, switching back to blue, 3 I minuses yields I3 minus plus 2 electrons. You okay? Now let me ask you a question. Oxidation or reduction? Oxidation, losing of electrons. We just figured out that the left-hand half reaction is our oxidative process. Now let's go over here. Switching back to red. Plus 15? Well, this is 18, but then here we've got 3 minus 1s. So this entire side, if I'm thinking correctly, is plus 15. Is that right? Okay. So guys, this side is plus 15, and this side is just minus 1, right? So guys, again, with the hands, this side's plus 15, this side's minus 1. So what do we got to do? Bring this down to minus 1. So what do? Add 16 electrons to the left-hand side. Oh, I want to switch. That did not count as a mistake. That was simply a color choice. 16 electrons plus 18 hydrogen ions plus 3 IO3 minuses yields I3 minus plus 9 waters. Ah. No! Ah. No, you're just nervous like me. So guys, let's talk about this now. Hey, so oxidation or reduction? Adding electrons in, right? And I know we're adding electrons here, but as a product, so they're going out, which is oxidation. Here they're coming in, so it's reduction. Guys, what about this? What if we had done this and we had found our extra electrons over here? We made a mistake because they both can't be oxidation. Once you know that this one's oxidation or reduction, you know that the other one has got to be the opposite. And if it's not, you screwed up. So now let's keep going. Next step, guys, multiply each half reaction so the electrons balance. So we've got 2 and we've got 16, so we have to multiply this by 8. So 24 I minuses yields 8 I3 minuses and 16 electrons. Now guys, at this point, I allow myself the freedom to not rewrite the other reaction, because now our electrons balance, and our next step, as you notice in our steps, is to bring these together. So at that point, what I like to do is draw a horizontal line. And now, guys, we are going to bring down all of the reactants and products. So let me switch colors. So my reactant here is 24 iodide ions. Then my reactants from the right-hand side, 16 plus 8 protons plus 3 IO3s yields, and guys, we're just, well, I really need that charge though. So it's just 16. These are electrons. I don't know why this won't write. Then guys, my products are 8 I3 minuses, 16 electrons, 1 I3 minus, and 9 waters. So 24 iodides, 16 electrons, 18 protons, 3 IO3s, 8 I3 minuses, 16 electrons, 1 I3 minus, and 9 waters. Okay. We're about to. So now what we do, guys, is we cancel stuff out. So the 16 electrons has got to cancel the 16 electrons. Why? Because that's what you did here by multiplying by 8. Then, guys, you compress everything that you can. So we have iodides over here, none over there. We have protons here, none over there. IO3s here. No, okay, so all we can do is bring these together. So guys, we've got 24 iodide ions plus 18 protons plus 3 IO3 minuses yields 8 triiodide ion. No. I'm about to cuss. I took my pen up. Thank you. 9 I3 minuses, and 9 waters. I can't count it. I know that for many of you, never mind, I was about to offend you. I can own it. I can own it. Hey, so guys, but we're still not done. Do you see why? They're all divisible by 3. So guys, this becomes 8. This becomes 6. This becomes 1. This becomes 3. And this becomes 3. And so then, guys, at this point, how many iodines do we have on the left? We have 8 plus 1 is 9. And over here, we have 3 times 3, which is 9. So our iodines balance. Then how many hydrogens do we have on the left? 6. And over here, we have 6. And then how many oxygens do we have? 3. And here we have 3. And that equation balances. Yeah. Okay.
And now you curl up into a ball of wave.
Yes. Or you do another one. No, the mistake has been made. Guys, I understand that you grew up in a culture where everybody gets a trophy, right? Everybody's good. Everybody's above average. You guys do understand this, right? We just handed out awards for high honor roll. We have 1,150 kids in this school, and more than 300 of them are on high honor roll. When everybody's special, nobody's special. Okay. Here we go, guys. So it goes like this. So, guys, you see now that this one is in a basic environment. You don't have to worry about that until the very end. But now we need to write half reactions. And guys, you'll notice that we have 2 products. So you just have to link them up. Obviously, copper doesn't become nitrogen. So Cu 2 plus becomes Cu. And then N2H4 becomes N2. Oh. The floodgates are open. Becomes N2. Okay, so you ready to do this? Step 1. Balance all of the equations other than oxygen and hydrogen. Done? Done, right? Don't rewrite them. Now, guys, the next step is to balance oxygens by adding water. Done. Next step is to balance hydrogens by adding protons. Done, but I would strongly encourage you to rewrite it. And then we've got N2H4 yields N2 plus 4 protons. Is the next step balance charges? Yeah? Okay. So guys, the next step is balancing charges. Here we have a charge of +2. Here we have a charge of 0. So we will be adding electrons to which side? The left, 2 of them. So 2 electrons plus copper 2 plus yields copper. Oxidation or reduction? Reduction. Then guys, over here, no charge +4. So we've got to bring that +4 down to 0. So we're going to go N2H4, N2, 4 H's, 4 electrons. And then, guys, at this point, we need to make the electrons balance by simply multiplying the left hand by 2. So 4 electrons, 2 copper 2 pluses, 2 coppers. Now we can bring these together. So we get 4 electrons, 2 copper 2 plus ions, an N2H4 yields 2 copper atoms, a nitrogen molecule, 4 protons, and 4 electrons. Am I doing okay? Oh, good. So then, guys, electrons have to go. I don't think anything else is combinable. Okay, so we've got 2 copper ions, an N2H, oh boy, an N2H4, 2 copper atoms, an N2, and 4 protons. So guys, now we need to talk. The solution that's represented in red, noticing these are aqueous, right? All of this chemistry happens in water. The solution that we have in red, acidic or basic? How do you know that this is acidic? Protons, right? Protons, an abundance of protons makes the solution acidic. But guys, that's not okay because we're told that this is in a basic environment. So what happens is this. The hydrogen ions that would otherwise be created by this reaction hook up with hydroxides and get converted into water. So what we do is we add an equal number of hydroxides to both sides such that we get rid of the free protons. So we're going to add 4 hydroxides to both sides. So we get 4 hydroxides plus 2 copper ions plus N2H4. Guys, I'm struggling, but plus copper plus nitrogen plus 4 waters. Now guys, making sure this balances, we've got 4 oxygens, 4 and 4 is 8 hydrogens, 8 hydrogens, that should be coppers, 2 coppers, 2 nitrogens, and that balances. So guys, there you have it. This is your opportunity to fiddle with these. We have about 5 minutes left. Making me especially glad that I printed notes.